Thank you very much. That was the best introduction ever. Uh, so I'm so privileged to get to represent the work of a ton of really brilliant people under Bud Frazier's leadership to develop the world's first practical permanent total artificial heart. It's on the 2-yard line for human testing. And I'm going to tell you where we've been, where we are today, and where we're headed. The list of people involved in this is too long to go into. Many of them are here in the room that have played a fundamental role in the development of this. But with no further ado, I'm going to kick into it. I'm not going to give any disclosures. We're totally conflicted. We have, I'll try to maintain some degree of equipoise, but I encourage you to put your appropriate filters in place. The artificial heart, as you know, is a very Houston story. It all started here, and now I think we're getting ready to plant another very important flag in this journey, and it's going to happen probably in the next week or two. And I'm going to tell you about how we got here. First of all, everybody in this room knows that heart failure is a big deal. We've all probably been touched by it personally. If you haven't yet, many of you will soon. It's a big, big economic burden. It's a big societal burden. Why don't we just transplant everybody? There just aren't enough organs. Last year, we did the most heart transplants in the United States that we've ever done, 4,169. And that's because we had more donors, tragically, because of the opioid pandemic. We now know that we can use hepatitis C positive donors. Allocation changed, so we were able to use more of the organs that were available. We have these transplant boxes that keep an organ happier and healthier for longer, so we can distribute them wider. And this new DCD, donation after cardiac death, that I never really thought would have an impact, but there were over 300 of them last year. Anyway, still at 4,169, woefully short of what we need. 160,000 conservatively Americans die every year of heart failure. It's probably closer to 350,000 a year. That's not a new idea. Michael DeBakey said in what year there'd be 100,000 patients walking around with that?
1980.
Yeah, he said by 1980, there'd be 100,000 Americans with artificial hearts. And he was working hard on making the first artificial heart with Domingo Leota. And you were involved as a medical student, weren't you?
Yeah.
Elaborate.
Oh, we put that in to Leota. Leota did all the work. Dr. DeBakey would come briefly. The main thing DeBakey did is he got the funding. And he got $5 million from LBJ in 1963, I think. 60. That's the most they've ever given anybody. Of course, they had 2 Texans, both of them sort of semi-con artists, and they got that huge grant, and it went to Baylor. And that's how Leota got here. That's how the first artificial heart got here.
And DeBakey and Leota were working on this project, and DeBakey had put it in 7 calves, and the longest calf went about 12 hours. DeBakey had recently brought in Denton Cooley from Johns Hopkins, who was rapidly emerging as the fastest and most technically gifted heart surgeon the world had ever seen. He really wasn't, I don't think he was interested in artificial hearts that much, but Leota said, I'm so frustrated. This is taking so long with Dr. DeBakey. Can't you help me? And he said, well, why don't you bring one across the street to St. Luke's and we'll look at it. Dr. DeBakey was frequently going to Washington, D.C. This is a picture from 1963 when he got the funding from LBJ, but this is now 1969. He's in Washington, D.C. again. And while he's there, what happened? What happened, bud?
First artificial heart. The problem with Dr. DeBakey, he did a lot of things. He built Baylor, but he didn't start doing cardiac surgery till he was 52 years old. And it required, particularly then, a bit of alacrity. And Dr. DeBakey was too slow. And that's why all the calves died. Dr. DeBakey said that time and again, well, he had no long-term survivors. Well, he didn't, because they were on the heart-lung machine for 2 hours or more. And you could take a young calf and put them on the heart-lung machine for 2 hours and not do anything, open their chest or anything. They would die from that. So anyway, and that's why Leota went over and convinced Cooley to put it in. And Cooley knew Dr. DeBakey wouldn't let him get through. He'd fire him. And the one thing he wanted for sure was to get out of Baylor and all the medical school restrictions. So it worked. It was the greatest idea he ever had, he said.
So here, April 4th, 1969, while DeBakey's out of town, Denton Cooley sews the artificial heart into a gravely ill patient, Haskell Karp. Haskell Karp tragically started hemolyzing on the device. He was on it for 64 hours. They then transplanted him. He died 32 hours later. But it was the first artificial heart ever implanted. DeBakey returned from Washington, D.C. and was very congratulatory and complimentary of Dr. Cooley. No, not really. He fired him and fired everybody in the lab. Dr. Cooley had come over here in 1962 and started the Texas Heart Institute. Everybody in the lab moved over here. It was widely publicized here on the cover of Life magazine, Time magazine, big TV stories about these two feuding titans, and they didn't speak for the next 40 years. But because their two hospitals were separated by a parking lot, it was almost like the Cold War, the US and the Soviets in the space race. Throughout the 1980s, the two of them together did more heart surgery than was done in all of Europe. They became the two busiest heart surgeons in the world. That device is actually sort of still with us today. This is how it worked. This is the device they put in April 4th, 1969. I was 8 years old. My mother cut out the article. I took it to school and showed it to a pretty girl sitting across the aisle from me. But it had two balloons hooked up with air hoses, and the balloons would fill and force the blood out. Then the air would be sucked out. The blood would come back in, and 4 valves turned it into unidirectional flow. That device, placed in Haskell Karp, is enshrined in the Smithsonian Institute. If you're ever there in Washington, D.C., go by and visit it. But its descendant is alive today. It's been called several things. It was called the Jarvik 7. You may remember that, Barney Clark. Then the Symbion and the Cardio West. It's now called the Syncardia Temporary Artificial Heart. And in the different versions, almost 2,000 of those have been implanted, and 70% of the patients are alive at a year, which is incredible because all those patients are facing death at the time of implantation. Here's the device. It's a temporary device. Why? You have 2 air hoses going through your body. It's not a great existence. It's got this box that's going chickum, chickum, chickum 100 times a minute, and that fails, but that's okay. When it fails, you can replace it. And they do. They replace that box every 3 months with a new one. But the real problem is this device that's in your chest. 100 beats a minute. That's 144,000 beats every day. That's 52 million heartbeats a year. No man-made device can do that without breaking. That's why airplanes with flapping wings didn't work. We had to come up with a better way. Okay? When this device would fail, you die within the next minute or two. And there have been some patients that have gone a long time with this temporary device, but the poor durability makes it so the average time you have one of these in your chest is 90 days while you're frantically looking for a heart transplant donor organ. We had a patient that I guess Igor implanted that went 4 years before one of his valves closed and didn't open again from cyclic fatigue, and he died acutely. The stroke rate is very high. It's noisy. The driver's heavy. Still, It saved a lot of lives. Others realized, look, having a backpack with a compressor and air hoses is not going to be a long-term solution. This is a device that Bud Frazier, working with Abiomed, helped develop. They spent $250 million. All the early work was done in our animal lab at B2 in this building, one floor down from here. I think you did like 150 animals. What'd you think of the device?
It was a good device. It never failed. It was just, it couldn't raise people from the dead. That was a big limitation, is most of these patients couldn't survive a hernia operation, much less total heart replacement.
But the big challenge was the durability, right?
Well, that's true. The bottom line was durability. Even that one, that's the problem with the flexing diaphragm. This patient that it failed at 17 months, they could tell when the diaphragm failed. And I asked him if he wanted another one, and he declined.
He had had several strokes. All the patients had strokes and infections. Of the 14 patients, only 4 of them lived longer than 9 months, and they all died when their devices failed. So it was a big device. It used a lot of power. Biggest problem was durability, though. Okay. So in 2004, the FDA said, well, you want to try some more patients? And Abiomed made a business decision, said, this is too expensive. This is too hard. And they gave up. So in 2004, it looked like we were never going to have a practical permanent total artificial heart. There's another organization out of Europe, CARMAT, that's still trying to do this. This is just like the AbioCor, the one I just showed you, but it's lined with bovine pericardium. It has valves made out of pericardium, but it is a big, complex device. They put 42 of these in, but 13 of them have failed and stopped working at 10 weeks or at 20 weeks, and the patients die immediately. 1/3 of the devices fail. It's huge. It uses a lot of power. There I am holding one with that's Piet. He's the chief medical officer of CARMAT. So we wish them well, but I'm going to change gears a little bit now and talk about LVADs. Bud, what can you tell me about these two devices? You guys all know these devices, right? This is the XVE on the left and the HeartMate 2 on the right.
Can you move this from here? Anyway, well, as Billy said, it became obvious to me that the postal pump would only be a bridge to transplant, and we didn't have enough donors as it was. I don't know. How do you make this advance?
You want to advance it?
Yeah.
Well, the next slide's just you.
Yeah.
So you can look at this picture, you can look over there. It's the same thing. Yeah, I'm advancing the slide. So what do you look at a picture?
Okay, well, as I said, the bottom line was how to get away from these big postal pumps. They were big. That was another limitation. Here you see one on, I guess, on your left, or and then we put in the Jarvik pump. There are several reasons why it wouldn't work. One is the high speed you had to move them, and that would hemolyze. And then the next, of course, was they had to have a bearing because they were axial flow pumps, axial flow. If an axial flow, you have to have a bearing, and a bearing has to be lubricated. So it can't get oil in the bloodstream, so it can't be done. Anyway, what's the next slide? I don't know.
Well, so the one on the left, the XVE, you put in like the first 25 of those before anybody else in the country put one in. And most of the patients in the earliest days wouldn't survive, right?
Well, the XVE was the same problem of the pneumatic. The pump you see there is the pneumatic. You could drive it pneumatically, which was a lot less expensive.
But big durability issues. It would last 18 months, 24 months on the outside.
Yeah.
It was to keep a patient alive while you're waiting for a transplant. That one on the right, the HeartMate 2, was the first commercially successful rapidly spinning pump. And there's a patient in San Diego that's had one of those for 20 years. They don't wear out. One moving part, suspended by bearings. Now we have ones that don't even have bearings. no flexible membranes, no valves. That changed the whole world of pumping blood. And as a result of that, Dr. Frazier, I was in Boston still. I had left. So I did all my medical school general surgery and cardiac surgery with Dr. DeBakey. I was here 11 years, but they'd all see me in short pants. I wasn't going to stick around here. So I went up to Boston to the BI Deaconess, got a Harvard faculty appointment. But Bud said, hey, Billy, why don't you come back down here and help me with this artificial heart? Anyway, he had the idea of leveraging rapidly spinning. That wasn't very good. Rapidly spinning. It always works a lot better if he's not around because you go, well, that didn't sound like him. And that's the guy he's trying to. Anyway, rapidly spinning pumps didn't wear out. Why couldn't we use those to rethink the artificial heart? And so Rob Jarvik had developed this little turbine. It was just another rapidly spinning pump that worked really, really well. And you put the first one of these in the world with Steve Westerby in UK, and did the first like 70 of them in the United States.
Put in 20.
Yeah.
And but anyway, it had bearings and it didn't need lubrication.
But it was a good pump. It was a great pump. And so Rob Jarvik was down here all the time. He was a weird dude, putting on his courses. And we said, could we get some of these? And he actually gave us 2 of these, and they were like $80,000 each. And we took an animal and we cut out its heart completely and put one Jarvik turbine in the left atrium and ran the graft from the left atrium end to end to the aorta, and then one in the right atrium and ran that end to end to the pulmonary artery. And here's that animal the next day eating hay, looking around going, why is everybody looking at me so weird? He had no heartbeat, no pulse. His heart has 2 moving parts, no flexible components, no valves. We were really excited by that and said, we got to try this more and more. In fact, I told Bud, I don't think it's going to work because the pressures and this and that. And I was wrong about that. But he realized that these pumps, any spinning pump, as the pressure at the inlet goes up, the flow through it goes up. So they could automatically adjust and keep the left and right side balanced, whatever the animal was doing. And that was like a Nobel Prize worthy eureka. So we did this a couple times, but the pumps were getting nastier and nastier. And Rob Jarvik wasn't going to give us any more because these were $80,000 each. So there was a company here in Houston called Micromed that Michael DeBakey had started. And tell me, is this true? Michael DeBakey was the NIH's reviewer of grants. And when Rob Jarvik applied for a grant for his rapidly spinning turbine, Dr. DeBakey said, well, you see, there's no opportunity for a spinning. This is a science project and probably not worthy of investing our nation's dollars. Turned down the grant and then started this company. Is that true?
Yeah. Unfortunately, that's true. And Dr. DeBakey, it was Lebanese, and he knew how to find a dollar, and so he started this great pump that was his idea, and it was just a copy of Jarvik's pump, and Jarvik was going to sue him, and I said, well, it's not going to work in the first place because it's positioned poorly. But in addition, I don't think a Jewish boy from New York suing Dr. DeBakey in Houston would get very far. And so I discouraged him for that.
Let's keep it PC. All right. So anyway, plagiarism is the highest form of flattery. So DeBakey paid Jarvik that incredible compliment and started this company. I realized there was an opportunity for us. So I went out there and managed to insinuate myself into this company as chief medical officer, which gave us unrestricted access to pumps since I was involved in that decision making. But this pump, we couldn't insert in the heart like the Jarvik's. The Jarvik was a nice, smooth bullet. This didn't have that sort of geometry or form factor. So we had to be a little resourceful. And so I went to medical device prototyping headquarters and I got drywall tape. That's the stuff you put on the drywall so when you paint over it, there's not a seam, and bath and tile silicone, and bought Dacron polyester from the fabric store and made these little conical things. My wife called them dolly dresses because they were all over the house. And we'd sew that little triangle into a cone, a C-O-N-E cone. And I would wrap it with layers of drywall tape and silicone, almost like a piñata, and got these structures that were soft enough that they could conform to the anatomy. We could trim them in the OR and they wouldn't fray. The needle holes didn't bleed at all because you're going through this tight multiple layers of mesh and silicone. And on the inside of the thing was Dacron polyester, the thing that DeBakey had shown us with his sewing machine that you could put inside in blood vessels. I made these adapters. We'd cut out the heart of a calf through a thoracotomy here. So one of these to the right atrial remnant after the heart's been removed, like a transplant, put a turbine on that. Here's a second one to the left atrial remnant. You got to cross them. So the left atrium goes to the aorta and the right atrium goes to the PA. Otherwise, it doesn't work well. And here's that animal 7 weeks later walking on a treadmill. No heartbeat, no pulse. Heart has 2 moving parts, cardiac output greater than anybody in this room. There's the legend Denton Cooley, Bud Frazier. I'm holding the molasses. We did this over and over and over again. Steve Parnas, you were part of all those operations. We learned something every time. It started getting very routine. And as a result of that, Bud said, here's a breakdown of the first 68 times we did it, the different pumps we did. And Bud said, well, maybe it's time we try this in a patient that's got no other attractive alternatives. We knew that if we sewed drywall tape and bath and tile silicone into a patient, we would go to prison and lose our medical licenses. Fortunately, there was stuff on the shelves back in surgical supply that were approved for implantation in humans, maybe not exactly in the way that we intended to use them, but specifically, instead of drywall tape, we'd use hernia mesh. Drywall tape was $5.99 for a 25-foot roll. This stuff was $2,500 a sheet, but pretty equivalent. Instead of the Dacron polyester that I bought at Joann's Fabrics, it was $27 for a square yard. It was about $1,000 a sheet, and NuSil silicone. And with that, made the world's first continuous flow artificial heart. The HeartMate 2 had just been approved by the FDA. And so I submit to you that everything in that photograph is approved for implantation in humans, albeit perhaps not in that exact configuration, except maybe that black band tie right here. I probably should have photoshopped that out. Anyway, we did exactly 2 cows with this continuous flow artificial heart, and then said, all right, let's wait for the perfect pitch. And this is Texas Heart Institute. Continuous flow of very sick patients come through here. We didn't have to wait long. A gravely ill 52-year-old gentleman with systemic amyloidosis came through. Very nice man, nice family. His heart was severely involved. He arrested over and over again. He was being maintained with the tandem support pump. He had amyloid in his liver and his kidney. He was severely icteric, severely jaundiced. He was in anuric renal failure on dialysis. He was in respiratory failure. And here is his post-op x-ray. We cut his heart out and put our twin turbine artificial heart in. And here he is post-op day 1, extubated, working on his computer. He was trying to come up with a way to have the 2 pump speed controls talk to each other. Brilliant guy, engineer. Tragically, throughout the next 5 weeks, his bilirubin continued to rise. He got so he couldn't stay awake. And at one point, actually started coughing up blood. And we did bronchoscopy on him and realized his lungs were packed with amyloid. And after some very challenging discussions with the family, the decision was made to terminate care. Brave man, taught us a lot. We got some great publications out of it. Dr. Frazier and I gave a TED Med talk in Washington, D.C. The coolest thing that came out of it, a lot of lay press descriptions. When I was little, I was always a science nerd and just geeking out to popular science. It was my first subscription that I had, and I would wait for that to come in the mail, and I just loved it. And so when we appeared on the cover of Popular Science, I said, man, mic drop, go home, wait for a happy death. What else? Um, Really, though, the coolest thing that came out of this was we met this brilliant, brilliant gentleman, Daniel Timms. He was 37 at the time. His father, so he was getting his PhD on a device that he had conceived of, an artificial heart, and he was doing it because his father was dying of heart failure. And ambitiously, and perhaps some hubris, he thought he could invent an artificial heart to keep his father from dying. His father got sicker and sicker and died while he was still getting his PhD, but that caused him to redouble his commitment, and he spent his entire life trying to develop this artificial heart. He didn't know us. We didn't know him. He was the only person he thought that thought you could make a continuous flow artificial heart. We thought we were the only people advocating that. We were coming at it from a perspective of heart surgeons at the Texas Heart Institute. He was a PhD, so most of the Australian surgeons didn't even want anything to do with him. He had never made a device that actually worked, but got invited to speak about it at a meeting in France, Singapore. Where was when Bud got up? That was in Paris, though, right? Or was it in Singapore? Yeah. So he was giving a talk in Singapore. Steve Parnas was there, heard about it, said, well, this is kind of interesting. And you talked to him at the time, told us about, hey, there's this kid in Brisbane, Australia, who's working on a continuous flow pump. Next meeting, Bud's at a big meeting in Paris. And Daniel, it's all surgeons presenting. Daniel Timms gets up and nervously describes his double-sided rotor that's going to be, actually, he didn't know it could be magnetically levitated then, but he described it. And Bud grabs his fedora, gets up, and starts walking to the microphone. And everybody's going, oh, this poor kid. Oh, no. Because when he goes to the microphone, it's not always a happy experience for the speaker. And Dr. Frazier goes, well, I don't know what the future of our field is, but I think it's going to be something like this. And Dan Timms was immediately a celebrity. Steve Parnas arranged for him to come down to Houston. He said, oh, this guy's got a great idea. And I said, yeah, I'm sure he does. We get a lot of people coming in with ideas. Listen, feed tuna fish mayonnaise. Most of the ideas aren't that impactful. So I had on my schedule a 30-minute block to talk to this guy. He had just gotten off the plane after a 14-hour flight. He had a backpack full of junk. He dumped it on my desk. I go. About 4.5 hours into our 30-minute meeting, I'm going, listen, you're going to bring the whole team down here and we're going to do this. We kicked our twin turbine project that we'd done in 68 animals and 1 human to the curb and totally joined Team Dan Timms. He brought these people down. We had no money. We needed $2.5 million, he said. I knocked on one door. Buy it today, sleep on it tonight. Gallery Furniture, Mattress Mac, wrote us a check for $2.5 million a week after I talked to him about it. We brought everybody down, and that was in 2012. And over the next 12 years, developed this device. You cut out the whole heart. This device has one moving part. This side pumps the bright red blood to the body. This side pumps the venous blood through the lungs. The whole moving part, the one moving part, is suspended by a magnetic field that's adjusted 20,000 times every second. It'll never wear out. There's no valves, and it'll outpump any 3 of your hearts combined. We've seen cows jogging on a treadmill with this in their chest with a cardiac output of 21 liters a minute. It didn't look like that at first. Like I said, it was junk. In fact, we had a journal. Remember, it used to have a journal bearing in it. Remember that? And it would turn the blood into Coca-Cola. But right after that, we realized it was magnetically stiff enough to be completely magnetically levitated. And the device lived on a computer as a digital file. So we could print it and iterate it over and over and over again. So here's a bunch of left-sided volutes and right-sided volutes. Here's a bunch of left-sided impellers and right-sided impellers. Each impeller, we did computational flow dynamics, so we designed them on a computer of what should work, but the proof of pudding is in the eating. We would take each impeller and each volute, print it, audition it, found the ones that worked the best. We then would actually make full printed plastic hearts. This has the motor in it. Here's the motor. You can see it behind this thin piece of printed plastic. Here are the magnetic levitation things behind this thin plastic. Here are the 3 eddy current sensors that are firing an impulse 20,000 times a second to instruct these 3 magnets how hard to pull on the rotor. Here's our rotor with a 3D printed best left impeller on one side, 3D printed best right rotor on the other side. This allowed us to take the pump and put it in a flow tester to see how it would perform. It allowed us to characterize hemolysis. And then in a very bold and somewhat creepy move, we sewed this 3D plastic printed heart into an animal. And here's that animal oblivious to the fact that his heart was printed on a 3D printer from Home Depot. One moving part. Now, this is no pulse. We could only do these for a couple days because those thin plastic walls would soak up blood and would warp. But this informed us what the real design needed to be. And then we went and became more sophisticated. But here's one of the big questions we needed to ask. Do we need a pulse? We'd done all these animals without a pulse, and they seemed to do pretty well. But it turns out, you know, if you look at your capillaries, none of you have a pulse in your capillary. That's where all the action is. That's where oxygen leaves, carbon dioxide comes in, nutrients come out, waste products come in. All of our animals without a pulse did pretty well. But if you got a narrowed artery, like a 50% carotid, the washout behind it, beyond it, is much better if you have a pulse. Okay, maybe that's a good reason. We have this thing with pulseless humans. They seem to have more bleeding from their intestines, and there are different theories about why that might happen. And it certainly would wash the pulse out better. So maybe a pulse would be a good thing. Well, who cares? We can make a pulse. We just change the speed. We go up and down 900 RPM once a second, and we get a 40 millimeter pulse, a palpable pulse. It picks up on the pulse ox. Should we call this a pulse? Who knows? But if you want to have discontinuous flow, if you want to have time variant flow, we can make that. So here it is with a pulse, and you'll see when I reach down and grab the graph, you can see my thumb and finger. I mean, it's a real pulse. And the animals with pulses didn't seem to care. It didn't cause hemolysis. The free plasma hemoglobins are just like in a normal cow. If you saw this monitor in an ICU, would you think that was a rapidly spinning thing that was changing its speed? Looks like just a regular arterial waveform of any mammal, including all the mammals in this room. The waveform characteristics are just like a regular pulse. So now, once we had it down and knew how it was going to operate, we printed it out of metal. This is a single sheet of titanium spheres, 1/30th of a millimeter in diameter. Using that same computer file, a laser goes through and melts adjacent spheres together. Does that for 12 hours. There's the printed titanium bivacor heart rising from the mist like Venus. This allowed us to do chronic implants, longer standing. Here's how big it is. The Diet Coke is a universal metric for volume in this field. Still have a drive line, but we'll get rid of that soon. Here we are in the operating room. There's Steve Parnas right there. Anyway, there's me. There's Rich Wampler, who sort of created the field. Here's the whole Bivacor team. There's Dan Timms, Nick Graytrex, Mateus Kleinheier. There's Nobu. Yep. Isn't that you? We have such an amazing army of brilliant people here at the Texas Heart Institute. You couldn't do this work anywhere else. And it takes this kind of team, these kind of resources, these kind of hardworking people, many of who are in this room to do this kind of work. And I'm so grateful to be here and part of this team. But these animals, again, go 2-3 months, act like completely normal animals by every metric, have cardiac outputs that are exceed the outputs of anybody in this room. Lance Armstrong riding up a 40-degree incline. Here's an animal at 3 months. He put on 78 pounds of lean muscle in 3 months as he grew. These are juvenile cows. They start off awfully young and they grow and exercise and do beautifully. And this animal has no heart. We cut the heart out, replace it with a bivacor. And so based on this, we started navigating the regulatory hurdles and having discussions with the FDA. These went on for over a year. They finally said, we want to see 5 animals in a row go 30 days. Here are those 5 animals that we submitted in the end of 2022. None of these animals were on heparin, Coumadin, aspirin, no anticoagulants. They all had great cardiac outputs. We had a lot of infections, but we were able to stave them off. But it was a real problem in these cows that lie in their own excrement and have lines that are sewed in. But we got this done. Throughout the next year, a lot of back and forth about histology and questions about some of the things they saw in histology. We did a couple more animals. We've now designed for manufacturing, is in the rearview mirror. We started making pumps, sterilized pumps. We've now, this is old, this is 50 animals. It's probably closer to 70 now because of training sites around the country. We had challenges getting to 30 days, but we got better and better at it. We've raised a lot of money. We just did another $15 million bridge today. We've had great interactions. We completed our submission in June of 2023. In November of last year, they said, looks good, start doing patients. Over the last 5 months, we've been traveling around, getting site initiation, having the doctors come here, implant in animals and human cadavers with us. The results are getting better and better and better. We had to get our trial insurance. We had to get our subject injury language, our clinical trial agreements, our budgets. It is a mountain of work. But we are now through the IRB at Texas Heart. The central IRB that we use, the WSG, the Western, is coming in Tuesday. So the end of next week, our site will be activated. We have 3 patients in-house right now, all that are decent candidates. We've had mock presentations of screening calls of what we will be doing once we're activated. We could have gone to any heart center in the United States. Do you guys want to be in the bivacor trial? They would have been all over it. We got to pick the 10 best. We're picked 4 that are going to be in this EFS trial. And our EFS trial is to implant the pump, keep the patient in the hospital for 2 or 3 months, and then transplant them. We don't think this is a bridge to transplant. We think it's instead of a transplant, but that's the first milestone or benchmark that the FDA wants us to do. And probably in the next week or 2, we'll be implanting this. We have 6 clinical devices that are sterile in Pelican cases, ready to go. I have argued for and prevailed that the first 3 will be here at the Texas Heart Institute, just because. And it's been the adventure of a lifetime and standing on the shoulders of giants who were standing on the shoulders of other giants. And I think this will be the first practical, permanent, total artificial heart. If it's not this, it'll be something like this. Continuous flow is the way to go. We can make a pulse. It's smaller. It uses less power. It's going to be durable. I want to end with one really cool picture. And some of you may have seen this, but it's so neat. DeBakey and Cooley fell out over the artificial heart, right? I talked about that. And the implant on Haskell Carp, and they didn't talk for 40 years. Well, Bud and I are both DeBakey products. He did his general surgery and medical school there. I did medical school, general surgery, and cardiac surgery there. So after these animals, we would go over and tell Dr. DeBakey what we were doing. What did he say? Do you remember, Bud, when we went and talked to him?
Oh, I had that idea a long time ago.
Yeah.
You know, that's academia, we call it. You always shuffle your feet, try to get
Yeah,
in position. He was a master of that. He never wrote anything or did anything.
You see, it's rewarding seeing somebody do this. I had this idea years ago. Anyway, for real. Anyway, but we would always say, why don't you come over and watch us do an implant? He'd say, well, I'll talk to Henny Bannon and see what's on my schedule. And several times we invited him and he didn't come. But then you had some discussions with him the night before. And I didn't know he was coming over. I'm down there getting the animal ready and putting on my headlight. And they go, Dr. Cohn, it's telephone. And I answer the phone in the little animal lab. And it's George Noon, one of Dr. DeBakey's closest confederates. And he goes, hey, Billy, it's Dr. Noon. Dr. DeBakey and some of us are coming over in the tunnel. I go, whoa. So I called Bud and he goes, is what? Okay. He called Dr. Cooley. Dr. Cooley says, oh, really? Well, okay, I guess I better come down. And we took Todd, your son, took this picture with his cell phone. There's Matthias Lobe, the German surgeon from Methodist. Here's me, here's Bud, here's George Noon, here's Michael DeBakey and Danton Cooley hanging out, shooting the shit, laughing like they've been great friends the whole time. Shortly after there, Dr. Cooley invited DeBakey to join the Cooley Society. Cooley invited DeBakey to join the Cooley Society. When Dr. DeBakey got his Congressional Gold Medal, he invited Cooley and Bud to go with him to Washington, D.C. And so not only does this continuous flow, practical, permanent, total artificial heart have the opportunity to cure some of the woes of heart failure, but it can mend severely fractured relationships. That's all I got. Thank you very much.